Okay, I think it's recording, right?
Yes.
Okay. Okay, do you need to do some additional testing or are you ready to go?
Um, I think I'm ready. Just want to turn off these
Okay.
subtitles. There we go.
Okay, great. Yeah,
Okay.
if you're ready, yeah, please
Looks
go ahead. Yeah.
okay. So, hello everyone. Good afternoon. My name is Kyle Beggs. I'm a graduate student in the Department of Mechanical and Aerospace Engineering. And today I'm going to be presenting a paper on COVID-19 diagnosis and more importantly, the prognosis. Okay, so and using a graph representation. Okay, so I guess we'll get started. Okay, so motivation. I think I don't really need to say too much regarding motivation for this project. I think COVID-19 has affected pretty much every single human on Earth these past couple years. So I think the implications of this work are somewhat obvious. Maybe some of the details that should be known, though, for some people who actually haven't gotten tested or never knew that they were sick or whatnot. So the main test that everyone gets, or the gold standard, is the PCR or RT-PCR to be more specific. But this is just a binary test. It just tells you if you're positive or negative, and that's it. That's all the information it gives you. So that's good for seeing, if you should quarantine or, things like that. But once you are positive and maybe you get to the point where you need to go to the hospital because you're having some trouble breathing or something like that, then it becomes important to get some more information, or in other words, to have the prognosis. So for those that are familiar with that term, I think it's more of a medical term. It just means the forecast of, or the likely outcome of the course of the disease. So basically how severe it is. Okay, so it's useful to then get a CT image, and this can actually provide a lot more detailed information. Kind of more of a, instead of this kind of continue or discrete return of a test return of just positive or negative, you can have more of kind of like a continuous I guess return. So this is really useful, especially for the logistics of the hospital. So you can effectively triage patients who are more severe that need to go to the ICU, or get a clue of maybe how many ventilators you're going to need soon because you just got some patients in that are really bad, or something like that. Also, saving time for the medical professionals is really important, especially in cases or in areas with COVID outbreaks. The hospitals are severely overrun with lots of patients and not enough staff. Okay, so that's also a motivation to for this work. Okay. So the problem statement is it possible to provide an accurate diagnosis, but more importantly, prognosis for COVID-19 patients just from the CT images. And so the authors aim to tackle this problem as a graph classification problem. So the objective is to simply classify if the patient is one of three different cases: a normal healthy, so that would be like a negative, a COVID-19 positive, but also really important is if they just have the common pneumonia. So most patients, the complication from COVID-19 is actually pneumonia, and that's what that's what most people actually really suffer from, not from COVID-19 itself. It's the complications from it, such as pneumonia. So it can look really similar to just common pneumonia, but there are differences. So that part can be a little tricky. And then furthermore, if the patient is COVID-19 positive, we want to provide the prognosis. So what's the severity, how far will they develop into critical illness and they need to go to ICU and all that. And then a second thing or second objective of this paper was localization. So this is helping the medical professionals with time. And so what they aim to do here is actually point out the relevant slices in the image that basically show or reveal the severity of the particular case. And this also has another side effect of that it's also more interpretable, which is really important in machine learning in general, but especially in the medical field. The physicians need to understand why a certain result is given. Okay, so there's three main contributions from this paper. Is the use of graph convolution networks to extract information from the slices in a hierarchical manner. And so this idea is that sometimes the slices are ordered by depth, which ones are closest to each other, but actually sometimes in some diseases you may actually have relationships between some slices that are actually not right next to each other, and that can be important. So that's what they aim to do in this first contribution, is kind of solve that problem. And the second is a new pooling method called distance-aware pooling. And this was kind of designed specifically for densely connected graphs, which is what they represent the CT image as. And then the last contribution is the method to localize the important or relevant CT slices for the radiologists. Okay, so the approach to the problem, like I said, is to model to use a graph convolution layer, but actually it's that's just the first part of it. The model is actually made up of two separate modules, so to say. The first is the graph convolution layer. I'm sorry, let me find the pointer on laser pointer. There we go.
Yeah,
okay.
yeah.
Sorry about that.
No problem.
Okay. Yeah. Okay. So the first is the graph convolution layer. So that's these three, this part of the diagram right here. And you have the pooling along with that. So a couple layers of that. But then the second module or part of the model is actually just a kind of classic MLP classifier. And so this MLP classifier actually is the one that actually makes the classification here. Okay, but it should be noted that both of these kind of modules, the graph convolution network and the MLP, are directly connected end to end. So all the weights throughout both modules are updated solely on the loss, the classification loss of the diagnosis and prognosis here. Okay, so it is kind of still like one cohesive model. They just directly connected them. Okay. Also wanted to mention, so how this graph convolution network is, or how the graph is constructed, is the nodes are each slice in the CT, and the weights on all of the edges of the graph is constructed using a cosine similarity of the features. Okay. And the features are just the pixels in the slice. Okay. I didn't provide background of graphs here because assume this is a graduate level computer science course. I think there's only one other mechanical and aerospace student. So sorry to that one student. I actually happen to know about graphs, but anyways, I just wanted to mention that. I just assume everyone knows about simple graphs. Okay, so moving on. Okay, so the next thing that they implement that's pretty important, I think one of the focuses and biggest contributions of this paper is this novel distance aware pooling. Okay, so we have a convolution and then we pool and then we do another convolution and then we pool again. So this kind of idea is not new, but the approach of the actual pooling is new. Okay, so this is inspired by the concept of a receptive field in regular convolution neural networks. So the receptive field is basically just the size of the region that determines a feature. So if you have like a 3x3 convolution in a regular convolution network, I guess it would be like the 3x3. I mean, that's for a single layer though. If you have multiple layers that you continuously change the size of the network, then the receptive field might actually be bigger or smaller depending on how many convolution layers you have back to back. So anyways, I didn't know what that was before this paper, so I thought I'd just explain that. Where am I? Sorry. Okay, yeah, so it's inspired by this idea of the size of the influence of a particular feature, in this case of a particular node in the graph. So they adapt this though to be used for densely connected graphs. Okay, so the idea is you use a radius actually to determine each node's neighborhood or cluster, whatever you want to call it. So this is similar to doing like a nearest neighbor search, but instead of like a k nearest neighbors, it can have any k, any number. It's the parameters determined on the radius or the distance instead of the number of neighbors. Okay, so then you get a bunch of these clusters, and you can score each cluster and take the top k clusters, which k is some hyperparameter that's chosen, and then you from those top k clusters, you can select a new cluster center and then pull the features of those clusters and then determine a new node connectivity. So this is the main idea behind this. Okay. Okay, and then lastly, for the last objective, the CT slice localization, the authors report that this is also a new method. So the idea here is to determine which slices are most important for the diagnosis and prognosis, and this is done actually in a weakly supervised manner. So that's an advantage. It doesn't require any annotation. Okay, so the idea here is that you repeat these steps for each cluster in the graph. So each cluster, like this green oval is a cluster and the red is a cluster, etc. So for each one in the graph, you occlude that cluster or you act like it's not there, and then you run through the model and classify the image using the MLP here, and then you calculate what the loss is, and then if you do this for all the different clusters, their kind of idea is that the scenario where that has the highest loss, that cluster that was occluded is probably the most important because it had the biggest effect on the loss. It made the network perform that much worse. So therefore, those slices must be the most important. So that's kind of the idea here. And then finally, the cluster center is determined of that occluded cluster of slices, like maybe this is an example of the cluster of slices. And then further, and then they're further localized, choosing another K slices, and that's just also another hyperparameter. Okay, so experiments. First thing I want to talk about is the data pre-processing, and then I'll explain the talk about the data set, and then what actual other networks it compared against and what metrics they looked at. So for the pre-processing, they took each CT slice and normalized it to 256 squared. And then they, in each CT image, they also only sample 48 CT slices. The paper actually wasn't too clear. One of the weaknesses, which we'll get to, why they do this. Obviously, this kind of implies that some CTs images have more slices than others. So we just kind of need to, sample it so that they're always the same amount of slices. And then the one thing to note is they have so each node is a slice in the CT image, but the features in that slice, you can just represent them as the pixel values, I guess, like flatten the array, the image array, but that would be kind of somewhat naive. So there's two different I guess pre-processing methods that they do for each slice. The first is they actually use this bottleneck layer from the Inception v3 network. So this is the Inception v3 network. And in this very last, towards the end of the network here, if you kind of zoom in, it's hard to see this next to last fully connected layer is called this bottleneck layer. And so they actually use this and in the feature map from this as like kind of like a pre-processing. And then the other approach is to actually do a wavelet decomposition of the slice, and then flatten that array and have it be the feature in the node. Okay, so that's the pre-processing. Okay, doing the time. Just pause one moment. I did want to ask how much time do I have to know whether I should speak up or
so
not?
may have like 10 minutes most.
More?
Yeah, 10 more minutes most at most.
At most. Okay.
Yeah.
I think we'll be good.
Yeah.
Okay, so the data set, they take this CT data set that's available. One thing I do want to note is that all three classes actually are relatively balanced. So that's a common problem in medical networks that's not really a problem here. So the data set also contains information on the prognosis, and this was like one of the main objectives of the paper, right? So that is important. There's notes on with each image, saying if they were admitted to the intensive care unit or they did eventually end up requiring a ventilator and things like that. So the splits of the training is 60%, or split of the data set, 60% training, 15 validation, 25 test. And what they do here that I actually really liked is they repeat these data splits starting from 20 random seeds and retrain the model each time from scratch. So you actually, I guess, get results that are data split independent. And then they take the max average and standard deviation of the test set accuracies. So just some of the hyperparameters that they chose to use 5 graph convolution layers and 2 layers in the MLP classifier. The K hyperparameter in that pooling operation is set to 0.8. and they use a negative log likelihood for the loss function. Okay. Okay, yeah, so here are some initial some results from these experiments. So kind of talking about comparison of performance of like a couple different things. So when you're looking at just the network itself, they report that against the baseline, which is a 3D ResNet 18 model, they report that it achieves a 2.4% better accuracy while having less than 1% of the parameters. So that part is actually pretty significant. Also, for the slice localization, they report this the ROC curve here, along with a couple radiologists. And if you look, kind of qualitatively or on the curve here, it seems that it's actually performs better than the radiologists. So that would suggest success. But when you do look at the numbers here, the precision and recall are the most like more importantly, not more importantly, but more strikingly, the precision is 57%. That seems kind of low, but I guess the radiologists, or this must be just like a hard task in general, because it seems to outperform the radiologists. Okay, and this is a table of the outputs, which we'll get to in the next slide here, because this table is more relevant for the comparing the pooling and feature or extractor methods, or the pre-processing. So when kind of comparing just upon the pooling, so using a graph convolution layer, all of them always the same, a graph convolution layer, but just different pooling methods. There's 4 different pooling methods, including theirs. 2 of them automatically do really bad because the training loss and validation accuracy. These 2 plots here, you can see that the standard deviation on these is very big. So they're kind of sensitive, and I think they have the authors reported there was problems with the computing gradients. So you're down to the one that they propose, this DAP and this HGPSL method, in which the accuracy of those 2 are pretty close. This paper's method just barely higher accuracy, but more importantly to point out is the time per epoch. So it's about runs about twice as fast. So that is still a win. Okay. So good performance. Also regarding the pre-processing, using the Inception v3 approach is just way significantly better than the wavelets. There's just no even comparison. Okay, now I point that out there. Okay, so some related work. So there are many papers on this. So I just kind of tried to condense into some takeaways. So the first approach is to use, try to provide prognosis just based on the macro health data. So that's just stuff like, your sex, age, blood O2 concentration, stuff like that. There's moderate success, but definitely all of the work using the CT images is performs much better. So there are a couple of papers also similar to this on using CT for the COVID diagnosis and prognosis. All of the rest do use, your typical convolution neural networks, though. One of them reports just 1% less accuracy than this paper, and the other reports actually better accuracy, but importantly identifies that the transfer learning in this problem can actually have a significant impact, which this paper always trained from scratch. Okay, so conclusion, the paper introduces a graph convolution based network, although it's has the MLP in there too, for classifying CT images in a and providing prognosis, but in a hierarchical manner. So, the idea here is that you may have relationships between slices that are not right next to each other. So they try to capture that. The PCR is useful, but prognosis is more important for logistics, especially in COVID. Overrun of the hospitals is important. So it's an important application of the method. Ultimately, the method outperforms the baseline in the learning objectives, and while being extremely efficient in doing so. They introduce a new pooling method and show that is a upgrade. Maybe it doesn't achieve better accuracy, but twice as fast is a significant boost for sure. And then lastly, they are able to actually provide localization to not only save time, but also strengthen the confidence in the results and improve interpretability. So that's important. Okay, so some of the strengths of the paper is that it's an important application. I think that everyone knows that. The method does perform significantly better than the baseline that they compare against. Their pooling method, I just mentioned this, is good because it runs faster while achieving same accuracy. They're able to localize the most informative slices in the CT, and actually performs better than the radiologists. Also, the paper was really easy to read and understand, especially for me, someone who I don't have a strong computer science background. So it was actually a really nice read. So that counts for a lot. So some weaknesses, there are several weaknesses. They do only use one data set to evaluate the model performance. So they really should be using more data sets. They just say, oh, we use, this many layers, and we use, this K number of clusters when doing the pooling method, et cetera. All these hyperparameters, they just like choose them out of thin air, and don't really explore or do like a hyperparameter search or sensitivity analysis or something like that. Performance of the localization seems to not be great, just looking at like the precision, although it seems to do better than the radiologists, which is interesting. We'll kind of come back to this actually in the future slide. And then also lastly, they only compare against one baseline. So just this 3D ResNet 18 architecture. And there's really a ton of different architectures that can do this, and a couple of the papers that I put in that relevant slides, in the relevant work slide, use a couple different CNNs as well. So they really should be including more architectures to compare against. So you kind of lose confidence in some of the results. Okay, so my overall rating, according to the NIPS rating system, is from 1 to 10, 10 being best, 1 being bad, is a 6, so barely accept. So I barely accept because the application is important and useful, and namely because the new pooling method, I think is pretty good, although not much better in accuracy. I think people don't put enough emphasis sometimes on computational efficiency. So I think, based on those things, it deserves a spot. But more testing does need to be done ultimately with more data sets and comparing to other networks. So there is some uneasiness about how much you actually trust the performance of the model. So that really detracts from the paper, although the initial results seem to be good. Okay, so some future directions, they need to test using more data sets and more networks. I think they can look into this localization a little bit more. I think this was an interesting part of the paper that seems to do better than the radiologist, but the typical, the actual numbers, the metrics don't seem that great, at least compared, to other tasks. So, why is that? Maybe it's a hard problem, or I don't know, but could be some interesting future directions. Also, there is such a difference in using the bottleneck layer from this Inception v3 net for the feature extractor versus the wavelets. So obviously that is important. So I think they should explore this part of the model more and compare using some other feature extractors that could be interesting as well. Okay, so I think yeah, that's it. So I hope everyone enjoyed. It looks like I'm just like a minute over. Sorry about that.
No problem.
So any questions or comments?
Okay, great. So yeah, thank you, Kyle, for the presentation. I think you set a very good example for the class. You did a very good job on presenting the details of the method, right? The problem statement, the method, and the result. And also really appreciate you have very detailed comments on the strengths, the weakness, and also provide some of the thoughts or ideas on the future direction. So yeah, just give a round of applause.
Okay, nice, thank you.
Yeah.
Okay.
Yeah, but I do have a few questions before we go to the student, for the questions. So it's like more general, this prognosis, like what kind of labels, because is it also translate to classification problem, right? For the diagnosis, I understand they have like normal and COVID positive and the like just the usual or common pneumonia. What about the prognosis? Like how many classes they have and what exactly are those labels?
Yeah, so the paper wasn't actually too clear on how exactly what those labels were for the prognosis. They just said that the data set did have here's data set info. They just said that the data set did have information on if they went to the ICU and the ventilator and stuff like that. So yeah, perhaps this is probably could have been included in the weakness slides. Some more specific information exactly. How did they go from, they did state there was that data there, but they didn't really say like what the exact classes were for the prognosis. So yeah, that's probably a weakness. Actually,
yeah,
should have included that.
Yeah, so I think that would be more clear or helpful. At least we understand better about this problem, right? And so maybe have a better understanding when they compare with the radiologist, like the decision they are making. Okay, and the second, I think, which I don't really quite understand, or maybe they need to justify, is the ResNet 3D ResNet 18 they are using as the baseline, right? So why specifically choosing this as a baseline, right? I mean, you can choose other like a 3D unit or maybe other larger network, right? Because they are doing this kind of efficiency comparison, right? Maybe their method gains some advantage over 3D ResNet 18, but maybe for other network, they may not gain these kind of, advantage. But I think the, ResNet 18 seems like a smaller network, right? So I think maybe that's one reason they chose this, right? Just to demonstrate if they are able to outperform the smaller network, then if you choose like ResNet 30, ResNet 50, or maybe other larger network, they have more advantage. But it's still, I think maybe should explain this more clearly in this setting. And I think also you mentioned this, right? Just only one baseline for the comparison. Maybe more baseline comparisons will be more convincing.
Yeah, that was definitely one of the biggest weaknesses I think in the paper is yeah, I mean, you compare against only one network, you're kind of like cherry picking your results, maybe. Maybe they did compare against, larger networks and saw that their method didn't perform as good, so they
Yeah,
just left it out.
yeah,
That would be cheating.
right.
So yeah, it's initial results, it is promising that it does perform better than this one, but ultimately it's not as convincing. Yeah.
Yeah. Okay. Another thing is their network is just using Inception v3 as a feature extractor, right? They are not actually
Yeah.
training that
Yeah.
part, right? Like end to end. So I think it would be nice if they also, have that, feature extraction part, built as end to end trainable. So maybe in this way can have better performance. So I think people, do this, right? Everyone do this kind of end to end trainable. But if you're just using the pre-trained network as a feature extractor, then there's maybe some limitation because the pre-trained may be used on natural image, right? It's not like specifically tuned for medical image data. So maybe
Yeah.
that's another one downside, which they could at least try doing this end to end, maybe, and see
Yeah.
how the performance goes.
I
Yeah,
see. Yeah, that definitely does make sense. Also it'd be like a three module end to end kind of thing
yeah,
here.
right.
Um, yeah.
Yeah,
Yeah, it was, they did say, yeah, it's just they're just using the layer that's pre-trained on ImageNet. Actually, I think ImageNet.
yeah. Also, another like their feature extractor is Wavelet. I'm not sure why exactly they're using Wavelet, which is kind of like is the handcrafted or hand engineered feature extractor.
Mhm.
But maybe they just want to throw some baseline for the comparison. But I think it will be more interesting to test like just the different deep networks.
Yeah,
Yeah.
yeah, agreed. Using the wavelets is kind of weak. I think they just wanted something else to compare
Yeah.
against. Yeah.
Okay. And two more things. One is so they list the training time for like per epoch, right? But I think yeah, training time it's okay. If you're able to reduce the training time, that's good. But usually, training you're done once, right? You can forget about it. You don't have to train again. So I think people more care about is the inference time, right? How quickly can you process one slice or maybe the 3D volume of the CT, right? And get
Yeah.
this conclusion of the diagnosis. So I think that's the most important thing here.
Yeah, but I mean, aren't these related? Aren't they going to be like scaled? Like,
Yeah, in a
the
way,
inference
right.
time of this one should be, twice as fast as the inference time of this one, though.
No, it's not exactly
That's naive to
well,
say,
yeah,
huh?
I mean training time um yeah, per epoch, yeah, depends on the network architecture, their features like inception or wavelet. But I think the more direct way to just to tell or measure, the speed of the network or complexity of the network is the inference, because that's more direct, right? So people care, or
Yeah.
at least the doctors are care about, right? So I cannot wait a long time for the AI model to process that and make decision, under very critical condition, right? The patient need immediate, diagnosis and make some treatment. So that's kind of on the, threatening situation. So I think that's more, kind of more direct way to do the comparison.
I see. Yeah. More direct is always better.
Yeah. And the last one is, I don't know do they provide visualization, right? When they select the slice, like why exactly, or maybe just do some analysis, right? Let's say their method is able to localize those slides correctly. And why is that? Maybe make some analysis on that point. I think that would be helpful, right? Actually show those slices and, explain why.
Yeah. So something similar to like what you actually suggested as the optional thing for the assignment 1, actually, right?
Yeah.
The like torch cam thing.
No,
Like that.
I'm not.
Is that what you mean?
No, I'm not talking about using grading cam to visualize, but I'm actually saying visualizing this because they have classification and localization, right? Slice localization. Just give it a couple of examples, right?
Oh, okay. I see.
What's the result of their localization, right? Maybe, present those slices and show, okay, maybe some of the, pathology or some of the patterns appear on those slices, which towards diagnosis, this is a positive case, and what kind of, prognosis condition, that is, right? So I think that would be more interesting, right? See, to visually or like qualitatively to, to measure, right? How accurate is their model?
Yeah, I see. Yeah, I agree. So I mean, one of the strengths I said about the paper was that it was easy to read and understand, but perhaps too easy. They weren't thorough enough with, well, I guess that wouldn't make it harder to read, but I mean, pretty much all of the images that you see in my presentation were basically all of the images in the paper. Like there was like no more. So so there's probably a lack of visuals.
So again, this is also when you guys do any of your research work, or maybe in the final project, this is something to consider, right? If you have this kind of particular task, or any task, showing quantitative result is important, but also it will be very helpful if you can present some visual aid or visual presentation to kind of like qualitatively show, right, or explain why the model make decisions and why its method works well. Okay. All right, so I think we don't have much time to further discuss, but for the student, do you have any questions?
Yeah, can you hear me?
Yeah.
Okay, so I see you gave this paper a 6. For you personally, like, is there anything they could have done? What are the strongest things they could have done better to like achieve maybe like a 2 or 3?
Okay, I'm not sure I fully understand. What were the strongest things they could have done better?
Yeah, like what are the things you would say would be like the most important things that brought this paper down?
Definitely the lack of testing against other networks is probably the number one thing that brought the paper down. That's what I would say would be the biggest weakness is the lack of how vigorously they actually tested the model performance.
All right,
thoroughly.
Okay.
Yeah,
sounds good.
Good question.
Yeah, that's a good question, and I agree. So the evaluation can be more comprehensive, right? From different baselines, and do some more ablation on their networks, parameter tuning stuff, and also maybe helpful to experiment on more data set. So I think also that maybe one significant point I would give like a maybe not very high score on the paper. Okay.
One thing I actually wanted to maybe this is like slightly off topic, but the rating system in your slides in like the second
Yeah,
lecture or
so
whatever it was, it's like reversed, right?
yeah.
Versus what? Okay,
Yeah, so
I
I
just
think the rating system, different conferences, they have different rating system,
okay.
different
I was so
scale.
confused for a second
Yeah, so
there.
but I think it's okay. So it's just
Okay.
other like CVPR, they have a strong accept, weak accept, borderline accept, then there's borderline reject and borderline I mean reject. So reject like the highest score, 5. Strong accept, the lowest 1. So they rate in this kind of order. Okay, but
Mhm.
that's not important. So
Okay.
okay, great. So we don't have much time left. So let's continue to the second presentation.
Let me share my screen.
Okay.
So I'm Ilkin. I'm a PhD student in the CS department, and I'll be presenting the big self-supervised models, advanced medical image classification. So the motivation of this paper, they're mentioning the problem is that all we know, just creating labels for the medical imaging, it's too time consuming and expensive. So they're trying to come up with a way to use the unlabeled medical images. And with this paper, the authors they were able to achieve an improvement of 6.7% in the top 1 accuracy and 1.1 in the mean IUC under the dermatology and the chest X-ray classifications. And in the paper, they're showing that the big self-supervised models are robust to distribution shift. And they also show that we can learn efficiently with a small number of labeled medical images. In a related work section in the introduction, they're mentioning that it's been like there are 2 common pre-training approaches that's been using commonly. One is the actual like the supervised pre-training on the large labeled data sets such as ImageNet. But in medical images, we don't have a lot of labeled data sets. So self-supervised pre-training using contrastive learning on the unlabeled data is more attractive because like they enable the use of the unlabeled domain specific images, and we are able to use learn more relevant representations. And after the pre-training, supervised fine tuning on a target label data set of interest is used. And fine tuning, just to remind, it's taking the weights of a already trained neural network and use it as a the initialization for a new model being trained on another data. So I will give a brief a summary of contrastive learning first, because that's what this paper is mostly on. So contrastive learning, it's a machine learning technique used for learning the general features of a data set without the labels by teaching the models just the see which data points are similar or different than each other. In this example, we can see that the cats are similar to each other, and a cat and dog, they're not similar to each other, they're different. And I will go over in 3 basic steps. So we can think about it. The first step is a data augmentation step. So for each image, we have an image, and we perform 2 augmentation combinations. It can be, for example, crop, resize, recolor, or resize, recolor, or crop and recolor, for example. And we want the model to learn that these 2 images are similar to each other since they're coming from the same image. And we call these ones as positive pairs. And the second step is feeding these images, the two images that we created, into a deep learning model. In the thing, like the method that they're using, it is SimCLR. So they're using a big CNN such as ResNet. So with these models, we create vector representations for each image. And the goal here is to like train the model in a way that it outputs similar representations for similar images, for example, like for the positive pairs. And the third step is the maximizing the similarity of the two vectors vector representations by minimizing a contrastive loss function. So we can think about these ones as a vectors, and the angle between those vectors will give us the similarity. If they're like aligned on each other, it means that they're similar to each other, and if they're like apart from each other, that means that they're not similar to each other. And this is the actual architecture. So here we are trying to maximize the agreement. So the approach that's been using in this paper, first they're using self-supervised learning on the unlabeled natural images, which means like they're not medical images. They're using ImageNet images. We have cars, animals, everything. And after that, we are doing a self-supervised learning on the unlabeled medical images, and a multi-instance contrastive learning, which they propose in this paper, if we have multiple images of each medical condition, like if it's available. So for example, they're using two different data sets. One is the dermatology images, and the other one is the chest X-ray images. If we have multiple images for the same patient for the like same medical condition, we are using all of them. But if we don't have, we are just like skipping that part. And the last step is supervised fine-tuning on labeled medical images. And again, we are using those two data sets. So for the, I will start with the framework for the contrastive learning. So this is the proposed equation in the paper. I will try to like make it simpler. So just like two things to mention in this equation. So the similarity here is the cosine similarity, which I mentioned here, basically the angle between two vectors we can think as. And then we have the T, which is the temperature scalar. And other than that, I'll be explaining in these slides. So let's say that we are trying to find the similarity of this image to this image. So we're trying to compute the probability that the like two augmented images are similar to each other. So here the denominator, it's the sum of the similarity of all pairs, including the negative pairs. Positive pairs are the like same image but different augmentations. So here we are also considering the negative pairs. So like they're obtained by creating pairs between the augmented images and the all other images in our batch. And here we are just wrapping this value around the minus log function. So minimizing this loss function, it corresponds to like maximizing the probability that these two augmented images are similar to each other. And after that, they're also proposing the multi-instance contrastive learning. So the reason why they're using this framework is because in medical image analysis, it's common to like utilize multiple images per patient to improve the classification accuracy and robustness. The images can be taken from different viewpoints, or under different lighting conditions, which makes the framework more robust. So for this one, if we like when multiple images are available, they use this framework. But if not, they're just taking this, and as I mentioned, they're augmenting and getting two different images and trying to maximize the agreement. Also, in this case, we only have one image, so we're just like applying augmentation and then trying to maximize the agreement. But here we have two different images for the same patient, same condition. So what we're doing here is we are getting two crops from the images of the same patient, and then we are trying to maximize the agreement between like these images. It is similar to the first one, but the thing is we are using different images rather than different augmentations of the same image. And how this works is, so in contrast to the SimCLR that I mentioned, to construct the mini batch of 2n representations, n is the batch size here, they randomly sample a mini batch of n bags of instances, and they define the contrastive prediction task on the positive pairs from the bag of images instead of the augmented one. And each bag here, the X1, X2 to XM, they actually they contains images from a same patient captured from different views, and the it can vary for different bags. So they make the algorithm really clear in the paper. And they are applying this to two different data sets. One is a dermatology data set, and the other one is the X-ray data set. And for the dermatology data set, they have 12,000 unique patients, and each case has 1 to 6 images. And in total, they have 27 classes. Actually, they have 419 unique condition labels, but they took the most common 26 and they classified the others as other, so that they have 27 classes. For the first part, for the CLR pre-training part, they're using this data set and also an additional unlabeled images from the same source, so they end up with this much of images. And for the second part, MICL pre-training, they only use the test data sets. And for the chest X-ray, they're using the GXperts dataset, which is a large open source dataset of X-ray images. And they're also using an NIH chest X-ray datasets, but they're using this just to evaluate the zero shots transfer performance. So the reason why that they're performing two different, they're performing their method on two different data sets, they both have the same problem, which is the imbalanced data for the X-ray data set and the dermatology data set. And then the pathologies of different restricted to small local patches. And also they're both like quite diverse in terms of the type of images and the label space and the task setup. So they are trying to show the generality of their proposed method, which is not too convincing to me. I will talk about it at the end. And they're using two different evaluation metrics, which is the top one accuracy, which is the conventional accuracy, and the IUC. It basically represents how much the model is capable of distinguishes between classes. When we have a higher AUC score, it means the model is better at predicting zero classes as 0 and 1 classes as 1. So I'll talk about the experiment and the results. So here we can see the comparison of the supervised and the self-supervised pre-training, followed by supervised fine-tuning using ResNet 50 and the ResNet 152 on the dermatology and the chest X-ray classification. So we can see that the self-supervised learning utilizes the unlabeled domain-specific medical images, and it outperforms the supervised ImageNet pre-training. In both cases, we can see that the self-supervised is achieving better performance. And here we see that the performance of dermatology, skin condition, and the chest X-ray classification model measured by the top-line accuracy in the area under the curve with different architectures. All of the models are fine-tuned using transfer learning from pre-trained model on ImageNet or only unlabeled medical data or pre-trained using medical data initialization from the ImageNet pre-trained model. So here we can see that when we are using a bigger model, we see better improvements. So here for the pre-training, we're only using ImageNet. Here we're only using the dermatology data set, and here we're using the ImageNet and then the dermatology data set. So as we can see, it improves when we just use a dermatology data set. But for example, for this case, when we use ImageNet plus the dermatology data set, actually the accuracy is kind of decreases, even though the AUC is increasing. And when we look at the bigger model, we can see that the improvement is higher. And also for the chest X-ray data set, we can see that they were able to achieve the highest one with the pre-training on ImageNet plus the CheckSpert data sets. So here we can see the evaluation of multi-instance contrastive learning that they propose on the dermatology condition classification. So they didn't evaluate the model for the other data set, the X-ray images, because they mentioned that they don't have multiple images for each patient. So evaluation would not be correct. So they're only using this framework on the dermatology data set. And here we can see that when we use the framework, the accuracy improves. And here in the table 3, we can see that the comparison of the best self-supervised models proposed the previous works, and then the supervised pre-training baselines on the dermatology classification. Here also we can see that they achieved the best accuracy with their framework, and also pre-training on ImageNet and plus the dermatology data set. And here we can see the same thing. They're not using their framework because they are mentioning that they don't have multiple images for each case. So we can see the evaluation of the models on the distribution shifted data sets, and shows that self-supervised training using both ImageNet and the target domain, we can see that it improves the robustness of the distribution shift. And here we can see the top line accuracy for the dermatology condition classification, and the supervised models under different unlabeled pre-training data set and varied sizes of label fractions. We can see the top one accuracy here and different architecture, the bigger architecture and the smaller one. And we can see that the MICLE ImageNet plus dermatology datasets performs better. So conclusion, this paper proposes an alternative strategy based on self-supervised pre-training on the unlabeled natural and medical images. And it shows that the self-supervised pre-training significantly outperforms the supervised pre-training. And the paper, it proposes the use of multiple images per medical case to enhance data augmentation for self-supervised learning. And self-supervised pre-training is as we saw, it looks more scalable than the supervised pre-training, since the we don't need the class labels. The future directions for this paper, it can be more comprehensive investigation of the optimal augmentations, since it plays a huge role, as we showed, like we're doing the augmentations on the images for each image. And another thing can be like seeing if transfer of the self-supervised learning from one imaging modality and task to like another, if that's possible, like how this works. My opinions about this paper, the pros, I think it was easy to understand and it had a logical flow, and the related work was well written, and it was easy to learn. But it was also because I had like a little background on SimCLR, I could say, and the code is not available, but the algorithm is clear enough, and we have the algorithm for the SimCLR, and after that, their framework is, I think, easy to implement since they're giving all the details. And the problem they're touching, it's a huge, like, important problem in medical images, which is good. And then I think the cons, so they're mentioning that the MICLE pre-training multi-instance contrastive learning pre-training, it's only applied on the dermatology data sets, since they didn't have enough cases of multiple views in the other data sets. So I was wondering, like, if they can't, even though like the data set that they used in the paper don't have multiple views, I'm just concerned if in real life we can or can't find multiple views for the X-ray data set. So they're showing the generalizability by using two data sets, but I'm just not sure if it's even like possible to use it on the X-ray data sets, just the multi-instance part. And there's some improvements on the tables, like didn't seem like huge improvements, like here, for example. So I don't know if that's a like big improvement on this task or not. So I was like concerned about that. And the paper is mostly on SimCLR. They're of course introducing the multi-instance contrastive learning, but if it is not applicable to like a lot of data sets, I'm just not sure how useful that can be. So I think the overall is a very important topic, problem in medical images. And even though the novelty is not like so significant, I believe like it's useful method since they achieved like better accuracies, and they outperformed the strong, like the supervised baseline pre-training on ImageNet, which is pretty good since they don't need the labels. So as I mentioned, I'm not sure if it's applicable in real life. So I would give this paper rating of 4, and these are the references, and thank you for your attention.
Okay, great. Thank you, Ilkin, for the great presentation. So again, give you a round of applause, although we were not
Thank
physically in the classroom. Yes, I think a very detailed presentation about the method and experimental analysis. Yeah, I think we talk about self-supervised learning in class as well, and I think this is a very important topic for medical image computing. They also touch upon the problem, right? We don't have a lot of labeled data. Then, to feed any of the deep learning, right? Because the data hungry, and this is the seems to be a viable solution to address some of the limited training data. So I think based on your comments, especially the weakness of the paper, I totally agree with all these 3 points, and I think those are my biggest concern. So yeah, so one thing, obviously it's a conference paper, and because of the space limitation, right? So you usually have 8 pages for the main text. So wouldn't expand like a journal, you can do a lot of analysis, more data set, right? More baseline. But I think to make an even stronger paper, so these 3 points are quite essential. So one is, we want to see if, different, type of data set, right? Although they have 2 types, right? Dermatology and also chest X-ray, but will also be interesting to, maybe test on CT and also on MRI, right? So these like very common, medical imaging modalities, right? If you're able to demonstrate, it is able to consistently, perform well, right? For the self-super learning as compared to like supervised transfer learning, I think they'll demonstrate the generalization ability. So that's one big, issue. And the second is, like you mentioned, the improvement is not significant. So especially, I think the first one, when they do the on the ImageNet, and then they also kind of fine tune on the like dermatology data set or checks expert, right? So this table 4, the last row, only have like 0.2 improvement. I don't think this is a significant improvement by any means. 0.2, it's quite small, unless maybe there's some, justification, right? Why this 0.2 is significant. Maybe there's a lot of data or something on the test set. But if we look at the training cost, right? So you have to pre-train on the ImageNet, then go to the checks expert. Do you really want to do this to gain only 0.2? Is it like worth to do this? Is questionable, right? So we definitely want to see a larger improvement, so that by doing this kind of 2-step kind of fine pre-training is a reasonable or a right way to go, because we can gain more improvement in term performance. But 0.2 is kind of, would say just too marginal to me. So, and lastly, the SimCR is like the very basic one. So for the self-supervised learning, there's also other like we mentioned in the class, right? Like SimSAM or like the MoCo, momentum contrast learning framework. So it would be good if there's also evaluation with another 1 or 2 baselines for self-learning, right? And demonstrate their strategy also works well. Then I think for these will be very convincing results, and also provide a very strong insight, right? So what is the good practice if you want to do improve the performance on your target domain data set, right? So these may be the a good practice for practitioners or researchers in this domain to try. So yeah, so overall, I think it's a good paper, but in terms of evaluation, maybe needs some more work to make it more convincing. Okay.
Okay.
Yeah, great. So any other comments from the student?
I have a question,
Yeah, sure.
somewhat of a clarification. So I'm confused at the novelty of their, I think, MICL method, because to me, it just sounds like contrastive learning. But in their particular case, the similar images from the same class just happen to be from the same patient. Is there a difference here that I'm missing?
As far as I understand, the only difference is like when we don't have multiple images for the same case, all they do is like use different images and like do the augmentation like a crop basically, and just feeding the same network with those images. Like rather than we getting two augmented images, we're just using two different images. So I also couldn't see a like novelty here. And I'm also like concerned about like if this is applicable, like if it's possible to have multiple images in each case.
Okay, so it's like an amplification when they don't have multiple from the same, like, quote unquote class.
Actually, when they have multiple images, they are only able to use this framework.
Mhm.
But if not, they're just using the regular contrastive learning.
Okay, yeah, I said my second thing backwards, I think. But yeah, that makes sense.
Oh,
Thank
yeah,
you.
yeah, yeah. Thank you.
Yeah, so I think this is another good point in terms of the novelty. So yeah, I would say basically this is just apply the usual CMCR for the most multiple instance contrast learning is just something they leverage from the nature of the data set, right? So for the ImageNet, right, like we only have like just a single from the single image. Although, but you know, because we don't have the label, we cannot take, we're assuming we don't know the label, so we cannot like take two images from the same class and trying to maximize the agreement. Then that would be like a supervised contrast learning, right? So, but here, I guess they just leverage the nature of the data set, right? Maybe one patient, you know, like have, in this case, they capture maybe multi-view or maybe like two shots of the same patient, same condition. And in this case, then you don't need to do augmentation, right? Because you already have some like augmented version, but with similar patterns, right? It's the same condition of the patient. So they can using this like a positive pair to just kind of maximize the agreement. But yeah, this is, yeah, I agree, this may not applicable to other data sets, right? So you just have a single image, then it just fall back to the normal, the original CMCR. So yeah, in terms of the techno novelty, this is quite incremental, I would say. So there's no new component proposed, right? Just multiple instant learning, just how do you generate a positive pair, right? Just do the augmentation or maybe taking from the data set itself. Okay. Okay, all right, so any other questions? Okay, so if not, we can end here. But I want to say, you know, thank you for the two presenters. So they made a very good example. So I think, you know, follow the, you know, the template I provide, so that can, you know, kind of organize your talk or presentation to help you present these, you know, details better. So Yoking, one suggestion I would make for your presentation is you probably should, you know, provide the source. I see there's like a CMCR like explanation. I remember that's one like a post I shared this. I mentioned in the class, so maybe you should like list on the original source when you
okay.
like those cat image, right? Just credit the original author. So
Okay.
that'll be a proper way to, acknowledge, right? Yeah, the
Yeah.
cat, this example, just provide like a link.
Okay.
You know, this is the source. So I think that's a proper way to acknowledge the source or the original authors. Okay. But just this is just a minor thing. Okay. All right. So, and for you and the cow, could you please upload the slides? So I think under the assignment, there's a like a presentation, right? There's a presentation slides, so you guys can upload there. That is for grading purpose. And second, I want to collect your slides then and post on the like a class lecture. So the other student can, you know, if they want to look into some details, they can check the slides, if that's okay.
Of course, yeah.
Okay. Okay, great. All right. Thank you guys. And we'll meet again on Thursday. All right. Okay. Bye guys.
Thank you.
Right. Bye.